My name is Francisco, and greetings. Information theory and coding. I'm the presenter. Assignment 1, Morse code, Huffman and Lempel-Ziv-Welch. Then question and answers. Introduction. Morse code was developed in the 1890s and 1840s by Samuel Morse, with significant contribution from Alfred Vail and Joseph Henry. The first public demonstration of Morse code occurred in 1844 when the message, "What hath God wrought?" was sent from Washington to Baltimore via telegraph. A Morse code runs with, like as shown, we have dots and we have these lines. You can represent alphabetical letters in Morse code using bits by mapping each Morse elements to a binary digit. The most straightforward approach is assign 0 to a dot, assign 1 to a dash. Each letter is then encoded as a sequence of zeros and ones that mirrors its Morse code pattern. For example, A dot / becomes 01, B dash dot becomes 100, 1000, C dash dot becomes 1010. This binary representation maintains the original structure of Morse code but adapts its digital systems, making it easy to store, transmit, or process using computers and other digital devices. A Python script for a Morse code encryption and decryption. I'll show it later as I finish my presentation. Efficiency or version of Morse code for the English alphabet. The average code length for Morse code using bits is about 2.5 bits per letter for English, because common letters have short codes and rare letters have longer ones. The efficiency of my Morse code bit encoding for the English alphabet is about 60 to 65%, meaning it uses about 1.5 times as many bits as the theoretical minimum for English text. Why I would not use Morse code for data compression? Reason: it has limited efficiency. Morse code is tailored for the English alphabet and it is typical letter frequencies, but it does not adapt to the actual data being compressed. Modern algorithms like Huffman, Lempel-Ziv, and Deflates analyze the data for patterns and redundancy, achieving much higher compression ratios. Not bit aligned. Morse code produces variable length codes which are not aligned to bits. This complicates storage and processes on digital systems which are optimized for fixed length encoding. No adaptation. Morse code cannot take advantage of repeated sequences or patterns in data, which dictionary-based and statistical methods exploit for much better results. Outperformed by modern methods. Algorithms like Huffman coding, LCS, and deflates are designed to maximize compression efficiency for a wide range of file types, not just text, and can adapt to the actual frequency of symbols in any dataset. Welch enhancement to the original Lempel and Ziv method. Pre-initialized dictionary. This allows the algorithm to begin encoding immediately, improving both speed and efficiency compared to LZ, which builds the dictionary from scratch as it processes the data. In LZ, each output symbol contains of a pair, a dictionary index, and the next character. Welch simplified this by outputting only the dictionary index for each phrase, which reduces the size of the output and streamlines both encoding and decoding. By eliminating the need to transmit the next character, LZW reduces redundancy and makes the process more efficient. The modification made by Welch enable LZW to achieve better compression ratios, especially for files with repeated patterns, and the dictionary quickly adapts to common sequences. The efficiency and simplicity of LZW leads to its adoption in widely used formats such as GIF images and the Unix compress utility, demonstrating its practical advantages over earlier Lempel-Ziv variants. We have a Python scripts for LZW encoding and decoding, and Huffman coding and decoding. This is the picture which we shall be compressing using the various compression techniques. Compression ratios and differences. Huffman coding. It is advantageous when there is uneven distribution of pixel intensities, assigns shorter codes to more frequent pixel values, and longer codes to less frequency ones. LZW coding. It looks for repeated sequences of pixel values, more efficient for images with repetitive patterns as it builds a dictionary of these sequences. comparison. When the image are shown above, we had a ratio of 1 for Huffman compression. For LZW, we have a compression of 0.68. For zip, we have 1, and DCT, we have a compression of 4.19. Decompression using Huffman. With the Huffman code, the image can be exactly decompressed so that every bit matches the input and every pixel is identical. Decompression using RZW, the original image file cannot be recovered because the image used many more colors than an initial dictionary could hold. After a certain point, the algorithm began creating symbols, which were themselves composition of area symbols. Conclusion: most images contain considerable spatial correlation. The discrete cosine transform DCT convert the spatial images into the frequency domain. DCT contain effectively decorrelate the image. High frequency data usually has low amplitude. Thus, quantization concentrates most of the energy into the low frequency components. DC performs quantization and finally encodes using Huffman coding. Thank you. That's my presentation on the assignment, question and answers.